Okay, let us take a look at section 2.5 from your book, which is talking about forces and equilibrium in space. So remember, space is going to be in R2 or R3. That means 2 or 3 dimensions. And this is going to be the coordinate system that is rectangular, also called Cartesian, from the philosopher René Cartes, or Carte, depending on where you're from. So he invented um, this, which is very useful because has the coordinate system that we are using in a lot of our problems in engineering science. And it's basically saying that you can place numbers with within the axis, and that you can apply transformations to those numbers, and the physics will hold together. So you can transform the numbers by scaling them, by rotating them. Actually, this is the basic concept in software modeling, or CAD. Okay, so always start from your Cartesian coordinate system. This holds units, so you can have meters, newtons, voltage, anything. And later on, if you go to engineering or science or even architecture, you can apply transformations to this in forms of matrices or in forms of tensors. Okay, but this is way ahead. For now, we're just going to learn how to do the equilibrium in space. So the concept of equilibrium space is that the summation, or all the components of your system, are going to be zero, and x, y, and z. If they're not zero, the system is not in equilibrium and is moving. So in dynamics, this is not going to be zero. But in statics, this course, this always has to be zero. What that means is that if you have a force going to the right and another force going to the left, for this to be static, these forces have to add up. And the easiest case is if they're completely horizontal, F1 equals F2. But in this case, it's not so straightforward because the angles are different. So in this case is what we do, that the components of x equals 0 and the components in y equal 0. All right, so that's the concept. Let's look at an example here. A 200 kilogram cylinder. So they're giving us a mass. So remember that this mass is going to have a force going down, and we have to decide where our coordinate system is going to be applied. It seems like it's going to be here. It seems to be, yeah, because their directions are based on, or the distances are based on those axes. So this is going to be our x, y, and z. Let me actually use a different color. So we're going to have x, y, and z. And this force going down, negative y, is, we can call it Fw. First, the force because of the weight is the mass times the gravity. Okay, and they're saying that this is being fixed by the cables AB. So they're telling that the force is going to start from A going to B and AC, so we can draw our force from A to B and from A to C, attached to the top of the wall. A horizontal force P, this force right here, is perpendicular to the wall, holds the cylinder in position. Okay, so if this force is not here, the cylinder will hit the wall. It might even crack the wall, and this whole structure would collapse. So they're asking what force is needed to hold the barrel, the cylinder, fixed, static, at a distance of 1.2 meters from the wall. Okay, so this is a very nice problem. It's easy and it will help us understand the concept. So first of all, we have to understand that the summation of forces will be 0 in x, y, and z. That's the first step. Second step is to determine where's the coordinate system. This is going to be my 0 because they're already telling me that everything's going to be referenced from those axes, from y, from z, and from x. Okay, so 1.2 meters away in x, 2 meters away in y, and point C has -8, oh sorry, -10 and +8 meters. So careful with signs. All right, and if we do that, we're gonna have a force P, a force AB, and a force AC, and also the force of the cylinder going down. So for now, just to show them the forces, we don't really have to care. We don't care about the signs at first, and we're just expressing all the forces. We have 3 cables and 1 weight, so we should have 4 forces. So that means that P, which is right here already given, P plus the force of the, because of the weight, plus the tension of AC plus the tension of AB, this is equal to 0. All right, so one of them or many of them could be negative, but this is how you express your forces. All right, so we know that we have to find the components in x and y and z of those forces. This case is pretty simple because P only has components in x and the weight only has components in y, but A and B have components in x, y, and z. And remember that to do that, we simply find the force that is holding times lambda, and lambda is the unit vector. So that's the other thing that we have to do, find the unit vector of AC and AB. And that's already down here for you to revise. So the force P only has, yes, P is only in X. So we have a PX. Force because of the weight is negative the mass, which is 200 kilograms, times 10 or 9.81 meters per second squared. Okay. If we go and use your calculator, we'll have 200 times 9.81 is 1962. This is negative, and J, and newtons. Okay. So we have two things, the force Px and the force Fw, which is in y. All right, now we only have to find the tension in AC and the tension in AB. So this is where we get to get the direction of AC and AB. So A, B, direction. That is also expressed as vector AB. So remember, you start by the head of the vector minus the tail. So in X, and it's right here if you want to follow along. So we're going to have in X is 0 minus the tail is at 1.2 meters in I, comma, and J is at 12 meters minus 0. Let's see. We're doing AB. AB is x is 0 minus 0 minus 1.2, correct? Oh, we're doing 0.8. No, sorry, not point B yet. So yeah, that could be confusing. Um, we're doing the direction of we're establishing what's point A. So this is the tail, the head minus the tail. So we have coordinate 12 meters minus 2 meters in J, comma, and in Z is tail, sorry, head minus tail. The head is at 12 meters in Y, and in Z is at 8 meters. And A is at 0. And this is at K. Eight meters minus 0 meters at K. All right, so this is the AB vector. So that's where you have most of the issues, and I actually have issues there too sometimes. So you have to be very careful. Okay, so this is minus 1.2 meters in I, comma, 10 meters in J, comma, and it's always good to put meters so you get used to knowing that this is a distance vector and not a force vector. The force vector is when we multiply the tension times the lambda times the unit vector. Okay, and this is 8 meters in K. All right, so now what we do is we find the magnitude of AB. And this is square root of negative 1.2 squared plus 10 squared plus 8 squared. So the magnitude of AB is equal to, let's see here, square root of, and we have 3 components squared plus, okay. So the first component is negative 1.2. The second component is 10, and the second component is 8. So that would be 164. 1.2 is 12.86. 12.86 meters. It's not meters squared, because this meter squared is canceling with square root. So that's back to meters. So this is 12.86 meters. Okay, so lambda for AB is equal to negative 1.2 meters divided by 12.86 meters in I. So you can see how it's going to cancel out, comma, 10 meters over 2.86 meters in J, comma, 8 meters divided by 12.86 meters in K. Okay, and that gives us, okay, so 1286 minus 1.2 divided by 12.86, 0.093, 0.093 I, comma, always has to be less than 1. And don't forget your minus. We always forget the minus. 0.77 J and 8. Zero 0.62. Okay. Alright, so this is my lambda AB. Now, what we have to do is get the force, but we don't know the force. The force is basically multiplying the tension AB, or the force through AB. This is the force through AB right here. So we don't get confused with tensions and forces. So force AB and force AC. Actually, no, that was correct. This is the tension. The force was applied on the rope. Well, if I put tension here, I hope we don't get confused. This is going to be the magnitude. Okay, so if you remember, we have to apply this is going to be the magnitude that is going to be multiplying each direction, and this resultant here is going to be the vector. So let's do it like that. So tension at AB multiplying negative 0.093 I, or actually we don't have to do the whole thing. Let's just do times alpha AB, and that is equal to, okay, so TAB, the tension through AB, times actually negative 0.093 I, comma, TAB times 0.77 J plus, or I like the comma better, comma, tension at AB times 0.62 at K. Okay, this is our vector component of the tension. All right, now we have to do the same thing for AC. So let's go ahead and try and do that. So let me go ahead and do it right here. AC equals, so it's going to be head minus tail. So in X, head of X is at 0, tail is at negative 1.2 meters, comma, head in Y is at 12 and is the same point as before for Y. So it's going to be 12 minus 2 is 10 meters, comma. This is the one that's going to change. So head is at, notice that this is positive Z, positive K. So this is going to be negative Z. So it's at head is at negative 10 minus 0. negative 10 meters. AC is that location right there. And yes, that's what we get. So AC equals negative 1.2 meters I, 10 meters in J, negative 10 meters in K. Okay, that always double check this part because this is the part where most students and most people get wrong. So be careful, that is the most difficult part. Everything else is pretty straightforward. Getting the magnitude is very simple. It's just the square root of negative 1.2 squared plus 100 plus 100 meters squared. That's 10 squared plus 10 squared. Okay, so the magnitude of AC is equal to square root of plus 100 plus 100 is 200 of negative 1.2 squared. 14.19. And what yeah, 14.19. Very good. 14.19 meters. All right. So the same thing here. Tension at AC is equal to the magnitude of the tension, AC, times lambda AC. And lambda AC is equal to the vector AC divided by the magnitude AC. So lambda equals 1419. Negative 1.2 divided by 1419 divided by 14.19 is negative 0.084. Negative 0.084. And I, comma, 10 0.704 J, comma, minus 0.704 because it was negative 10. So it's the same value but with a negative sign. Okay, double check. Yeah, so far so good. So the only thing we have to do next is get our tension. So our tension AC equals T AC times lambda AC. So it's basically multiplying by each component. All right, so this is the moment where we do our summation of forces. So summation of forces in X equals, what do we have in X? We have that Px plus, actually it's saying that is minus, so minus TAB, or actually before we do that, let's go ahead and do this. So, and here we have a px, we have no y. For AB we have a px. Where do we do that part? AB, yes, we have a px right here. So it's negative 0.093. And then in X we also have a component for AC. So T AC equals 0, whoops, times 0.093. 0.084. Which component is that? This component right here. Equals to 0. All right, summation forces in y equals, let's do the same thing with blue. We have AC, we have a component, we should have a component in AB, which we do, and we have the component of the weight, which we do. So negative 1962, negative 1962 plus TAB times 0.77 plus TAC times 0.704 equals to 0. Let's move this around so we don't get confused on the when you open the file again. Okay. All right, and then for forces in Z equals to 0, we have negative, we have NAC is negative, yep, NAB is positive, and we don't have the P or the weight in Z because Y is the vertical component. Z is coming out from Z is this direction right here. So Z only has component for tensions AB and AC. Alright, so what we have is a positive component from AB, which is 0.62. So TAB times 0.62 plus, actually minus, TAC times 0.704 equals to 0. So one thing is that notice that I didn't put I, J, K because this is I, this is J, and this is K. The other thing is that I didn't put the units, but by now we know that all this is in newtons. That is in newtons, and the tension here is in newtons. So all these lines are in newtons. Okay, so what we have here is three equations, three unknowns. We have Px, TAB, and TAC. And we have three equations. Therefore, we have to solve these equations. And the way to solve those equations is with a calculator or with a system of equations online. So let's get that done. So to compute this, you can either try and do it by hand, which will take a long time, or we can go to Wolfram Alpha and do system of equations. All right. So here, what we need to do is that we need to set up the system of equations like so. So we have three equations, three unknowns. The variables here to solve for are x, y, and z. So in our case, the variables are, well, let's just do that. So let's do px, let's map it to x, tension in AB, take it to y, and tension in AC, take it to z. This is only so that we can use the calculator online and we don't have to solve three equations, three unknowns. All right, so let's go ahead and do that. So px is 1 times px. So let's type here 1 space minus 0.093 minus 0.084 equals to 0. Okay, then we have no px here, and actually we can take 1962 to this side of the equation, 1962 positive. So no px, therefore we have 0. Y is TAB, so it's going to be plus 0.77 plus 0.704, and then we have no px here, therefore we do 0.62y, 0.62 minus 0.704. That is equal to 0. So calculate. Okay, and we get the exact solution. So the exact solution. Right, first of all, did we do this correctly? 1x minus 0.093 minus 0.084, 0 plus and plus 0 point minus. I think there was an issue there. Okay, so let's go ahead and y is looking x minus 0.93 minus 0.084, 0.77 plus 0.704 y, 1962, 0.62 minus, oh, it's not 700, it's 0.704. Okay, compute. All right, that makes a lot of sense now. All right, so how much is this number? Calculator. All right, so we have 7207,407 divided by 30580. That is 235.7 newtons. All right, so Px equals 235.7 newtons. Okay, we're good. Let's go and do the next one. 196200 divided by 139 divided by 139, 1411.5. 1411.5. And TAC equals 3801375 divided by 3058. 1243. All right, so we're pretty close. Okay, so first of all, notice that all three forces are positive, even though we had negative signs in the system of equations. And that is because all three forces are in tension. Okay? Second, notice that when you do the system of equations everything was zero except for this number. So when you solve the system of equations, be careful that not everything is zero. Otherwise, this will be the homogeneous solution, that all the variables are zero. At least one of them has to be different than zero. And typically, those are forces that are given, that the problem is giving you the known force already, or the weights, which in this case is the force that is given. But to solve the system of equations, you have to set up the equations in x, and y, and z. So it's usually going to be three equations, three unknowns.